Hi guys, in this video we will look at the amazing Bernstein-Wasserani algorithm. This algorithm tries to address this challenge of finding a secret key embedded in a function. We'll take this particular function f of x, which takes an n-bit input x, and this function has a secret key, n-bit secret key within this function s. What happens is individual bits are multiplied or ANDed. Right? So x0 is multiplied with s0, x1 is multiplied with s1, x2 is multiplied with s2, etc. And the result is all XOR together, producing a single bit output. So for an n-bit input, we get a 1-bit output. The task at hand is to find the secret key S. So as a first step, let us see how we do this classically. How can we solve this classically? Classically, it is quite straightforward. To find a particular bit in the secret key, it's quite easy. If I want the first bit in the secret key, what I do is I'll give an input 1 0 0 0 0, every other bit is 0. So because every other bit is 0, the dot product of this, when I multiply 0 with s2, it is going to be 0. So everything else is going to be 0. The only one which is not going to be 0 or maybe 0 is this bit. So this bit is going to be multiplied with s1, 1 into s1. If s1 is 0, the result will be 0. If s1 is 1, the result is going to be 1. So this gives us the answer for s1. But that gives us only 1 bit, right? We give this input and look at the output, and if the output is 0, we know s1 is 0. If the output is 1, we know s1 is 1. But that doesn't give any information about s2, s3 up to sn. To get s2, we need to give a different input, which is 0. That particular bit is 1, and everything else is 0, right? So similarly, to get this in a classical computing scenario, we need to do it n number of times with n different carefully crafted input, right? Now, let us see the quantum side of this. What we claim is that in quantum magic, or in the quantum implementation, or when you try to solve this from the quantum computing, we can reduce the number of steps. We can reduce the number of steps, not just n is going to be n minus 1 or n by 2 or root n. We can reduce it into one single step. We can find the answer in one single step. That's the quantum magic. Why it happens? It's because we can put the inputs in a superposition state where we can input all the possible inputs to this function at the same time. So we give all the possible input to the function at the same time, which means we'll get all the possible output in the output bit at the same time. And we amplify only the answer that we want and not the answers that we want to find the correct answer, which gives us the secret key, right? This is a bit tricky to understand. So let us first see the implementation of this, and then maybe in another video I will explain why exactly this magic works. The first step to do this is to implement this function f of x in a quantum world, in the quantum circuit. Right? Technically this is going to be a black box. You'll get a black box of f of x, and you can give inputs and outputs and see give inputs and observe the output, right? But someone has to create f of x, right? So when you are trying this out, you may have to create your own f of x. So let us take an example with 6 bits. So these 6 bits are input, and the output is in the 7-bit q6. Q6 will be the output where we can expect the output. So how we do it is that very simple. The implementation is very simple. If the secret number which has to be stored in this function f of x is 101101, which is 101101, because q5 is this bit 1, q4 is this bit 0, right? q0 is going to be the least significant bit, this one. So if you want to store the secret number in the function f of x and do a bitwise inner product with the input. So input comes at these bits. When I give inputs here, this function basically does an inner product and give the output here, right? The first assumption is that the output bit is initialized to 0. If the particular bit is 0, secret number's value is 0, then we don't do anything, because that is not going to have an impact on, that bit is not going to have an impact on the output, right? Because that 0 multiplied by any input is going to be 0. So we only take the 1 bit inputs. So this is going to be 1, right? If this is 1 and if the input is 1, then this will be 1 into 1 is going to be 0. This initial 0 is going to be switched to 1. So we just need to have a control X operation wherever 1 comes, right? So wherever 1 comes, we just need a control X operation. So if this bit is a 1, you flip this bit, the output bit. So there you get the f of x. If you give an input here, you get the output f of x here, right? So let us see how this works in this simple example. So we give an input 1 1 1 0 0 1, right? So 1 1 1 0 0 1, when it is when inner product operation is done with 1 0 1 1 0 1, we will get the result 1. So when we measure Q6, we get 1, right? So we don't know what's happening here inside. Let's assume that we don't know. This function is given, this block is given to us. This input 11001 is given in such a way that, this everything is initialized to 0 first. I am putting an x gate here, so that Q5 becomes 1, Q4 becomes 1, Q3 becomes 1. Then there are 2 zeros here, and Q0 is also 1. With this input, Q6 is initialized to 0. We get an answer in Q6, which is 1. So f of x is implemented in the quantum world, right? So now we have f of x. What we need to do now is to see the quantum magic. How can we do this in one go and get the answer? This is a circuit for that, right? So we have the f of x here, right? So we have the f of x here. The input that we give is all 5 bits. We put Hadamard gates. This is called a Hadamard transform or a Fourier sampling. When we do this, what happens is, at this point, we have all the possible inputs, because Q0 can be, is 0 here, 0 and 1 with equal probability. This is also 0, 1 is also 0 and 1 with equal probability. We have seen this in initial videos. So each of these bits can be 0 and 1, which means this can be 0 0 0 0 0 0 0 0 0 0 0 0 1, 1 0 0 0 0 0. All these possible values can be the input to this circuit that we are going to give, which means at this point the answer can also be the answer of all these different inputs, right? And once we have that, we also put a Hadamard gate at the end, because Hadamard gates are reversible. So we need to reverse it to get the answer. And we do a very cheeky thing to put an X and H gate here. What it does is, instead of putting Q6 as a 0, we put it in a state called minus, which is 1 by root 2 0 minus 1 by root 2 1. Right? That's the only cheeky thing that we do. Once we do that, what happens is, as I said earlier, everything over here is all possible inputs in equal probability. All possible outputs in equal probability comes at Q6. And we have a superposition state of the secret key at this point because of this, right? Because we put Q6 in a minus state. And what happens here, when we have a superposition state of secret key here, when we put the Hadamard transform, it recovers the secret key and we get secret key in one go. So if you look at here, I haven't run the circuit multiple number of times. It is just one shot, which means this is run once. I put the input, all the input in the state, and then executed the circuit one time, and the answer that I got is 1 0 1 1 0 1. This is what happens in Bernstein-Vazirani algorithm. It's a very interesting algorithm. I know there are questions because I didn't explain why this happens. Okay? There's a bit of maths there, but it's very easy mathematics. We can figure that out. I will do a small video on that in the next video. I can give you a clue. Why this happens is because I initialize Q6 to a minus state. Right? When I put a Q6 to a minus state, this magic happens. So if you can figure that out yourself, great. If you can't, just wait a couple of days for me to put the next video explaining why it happens. Thank you. I hope you had fun in learning this. See you soon.